So yeah, that is what's coming up with how few people it looks like there are here today. I had several people letting me know that we're going to be absent. I think I might skip the lab this week. And we'll just continue on. There's enough space in the schedule that we can afford to skip it this week. We're just about to start chapter 5. Yeah. Yeah. There's like a handful of slides in chapter 4 left, and then we're starting chapter. Yeah, I think because there's so few people here today, and so all the people have to make it up. I think I'll just skip it for today. Unless a whole bunch of people come, I'll see where we're at the end of the lecture. But I'm thinking that I'll just skip it for today because also that'll match up with the lecture a little better with the labs. So just finishing off chapter 4 for general launch angle in general. If the initial velocity in the x direction is the initial velocity times the cosine of the angle. The initial velocity in the y direction is the initial velocity times the sine of the angle. So you get these equations of motion for a projectile. Some key characteristics for projectiles. The range. If the initial and final elevation are the same, the range is the velocity squared over g times the sine of twice the angle. You can get that by this quick calculation. The vertical position is the initial vertical position plus the initial velocity in the y direction times time minus 1/2 gt squared names. And then, sorry, why am I not? I'm having trouble hearing you. Yes, Lauren, okay. Hmm? Just those are graded lefts. So if we plug in our, and assume that y0 equals 0 and the final y is also 0, we can solve for time. So v0 times sine theta t equals 1/2 gt squared. So t is going to be 2 v0 sine theta over g. And then we can plug in also our numbers for x. X is x naught plus v naught cosine theta t. And then we can plug this t in. Okay, so everybody's just late today. And Ellie Sims, right? So if we plug in this, we get this for range. That can be rearranged to v naught squared times 2 sine theta cosine theta. V naught squared over g times 2 sine theta cosine theta. And there's a trig identity that lets you know that that range is v naught squared over g times sine 2 theta. So the range will be maximum when theta equals 45 degrees, then the sine of 2 theta will equal 1. So that'll just be v naught squared over g. And here's some examples of projectiles with multiple angles, all starting with the same velocity. And if two angles add up to 90 degrees, they'll have the same range. And I'm not going to go through the calculations for that. I'll leave that as an exercise to you if you want to figure it out. Also, paths of projectile motion are symmetric. So you'll reach maximum height at half the time. Half your air time if you're going from if you're firing on level ground, at half your air time, at half the time you're in the air, you will have perfectly horizontal movement, and your speed on the way up will equal your speed on the way down at the same height. So your speed here, so this and this, same speed, just the angle instead of being plus theta is now at minus theta. So here is a question. If two cats are sitting side by side on a fence when they're startled by a dog, they jump off the fence with equal speeds, but different initial angles. Cat 1 goes up at 45 degrees, arcs along, and eventually lands on the ground, while Cat 2 jumps down at 45 degrees below the horizontal. Is the landing speed of Cat 1 greater than, less than, or equal to the landing speed of Cat 2? Does anyone have a thought on this? Equal. Equal is correct. So basically what happens is the landing speed of Cat 1 is equal to the landing speed of Cat 2. That's because Cat 2's path, so Cat 2 is going down at 45 degrees. Once Cat 1 is returned back to the same height it was at, it will also be going down at the same speed that it left at 45 degrees. So these two parts, Cat 2's path and this end part of Cat 1's path, are identical. So once Cat 1 is returned to the height of the fence, it's moving with the same speed and direction as Cat 2 at launch. So both cats will have the same landing speed. So here we have an archerfish, which hunts by dislodging an unsuspecting insect from its resting place with a stream of water it expels from its mouth. Suppose the archerfish squirts water with an initial speed of 2.3 meters per second at an angle of 19.5 degrees above the horizontal. When the stream of water reaches a beetle on a leaf at a height of h above the water's surface, it is moving horizontally. How much time does the beetle have to react? What is the height h of the beetle? What is the horizontal distance d between the fish and the beetle when the water is launched? So remember, y equals y naught plus v naught for projectile sine theta t minus 1/2 gt squared. Vy equals v naught sine theta minus gt. X equals v naught cosine theta. It's x naught. Y squared equals v naught y squared plus v naught sine theta squared minus 2g theta. So, first question is, how much time does the beetle have to react? Well, notice that this mentions that the water is horizontal when it hits the beetle. That means its vertical velocity, y velocity, is 0. So to figure out that, we can use, so we know our initial position, which is x equals 0, y equals 0. We know our initial angle. We know our initial velocity. We know what g is. We know our final velocity. It's 0 meters in the y direction. That's 0 meters per second because it's moving horizontally. And we want to find time, our y position, that's the height, and our x position, that's d in this. So if we start with finding time, we can use this equation. Velocity in the y direction is initial velocity times sine theta minus gt. And we know our final velocity is 0 in the y direction. So 0 equals v naught sine theta minus gt. So in this case, time will equal v naught sine theta over g. So 2.3 meters per second times the sine of 19.5 degrees over 9.81 meters per second squared gives us a time of 0.0783 seconds. Then if we want to find the height of the beetle, well, now we can use this equation to find the position at 0.0783 seconds. We can plug in time. So y naught is 0, v naught is 2.3 meters per second, theta is 19.5 degrees, t is 0.0783 seconds, minus 1/2 times 9.81 meters per second squared, times 0.783 seconds quantity squared. That gives us a distance of 0.03 meters. And then lastly, if we want to find the horizontal distance, so the height was 0.03 meters, the distance horizontally is just going to be x is x naught times v naught cosine theta is x naught plus v naught cosine theta t. So x is going to be 0 plus 2.3 meters per second times cosine of 19.5 degrees times 0.0783 seconds, which comes out to 0.170 meters. So it goes 3 centimeters up and 17 centimeters over. Any questions about this? The important thing to notice here is because it's moving horizontally, that tells you you're at the peak, and so your velocity in the y direction is 0. So that's the end of chapter 4. So in summary, components of the motion in the x and y directions can be treated independently. In projectile motion, the acceleration is negative g. It's g downwards. If the launch angle is 0, the initial velocity only has an x component. The path followed by a projectile is a parabola. The range is the horizontal distance the projectile travels. And that was a quick summary of chapter 4. And there's various equations throughout. So we talked about describing motion. Let's talk about the causes of motion. So we're going to actually start talking about forces. I'm going to erase these equations. So we're going to talk about Newton's laws of motion. So here we have a sled being pulled by 2 people. It has 3 forces acting on it, and there's a net force in this direction causing an acceleration. So we're going to talk about force and mass. We'll go through all 3 of Newton's laws of motion. We'll talk about the vector nature of forces, how we deal with forces in 2 dimensions. Then lastly, we'll talk about weight and normal forces. So a force is a push or a pull. And it's a vector. It has a magnitude and a direction. Because, I can apply a force this way into the wall, or I can apply a force this way into the wall. The various other things. Right? Any force has a magnitude and a direction. So here, this force, he's pulling on the string up at some angle theta, and that's providing the force. Now, the force interacts with mass. Mass is a measure of how hard it is to change an object's velocity. It can be a measure of the quantity. You can think of it as a measure of the quantity of matter in an object, but it's also a measure of inertia, how hard it is to change an object's velocity. So more massive objects are harder to change the velocity. They want to keep doing whatever they were doing more. So some example masses of objects. Let's start at the big. The Earth is about 6 times 10 to the 24 kilograms. The space shuttle was about 2 million kilograms. A blue whale, the largest animal on Earth, that's about 105,000 kilograms. A whale shark, the largest fish, is about 18,000 kilograms. An elephant, the largest current land animal, is about 5,400 kilograms. A car is usually around 1,200 kilograms. It's a little more than a ton. An adult human is something like average adult human is maybe 70 kilograms. It varies. I, as an adult human, am quite a bit more than 70 kilograms. But a gallon of milk is 3.9 kilograms. A quart of milk is about 1 kilogram. A baseball is about 0.145 kilograms. A honeybee is 0.00015 kilograms. And a bacterium is about 10 to the minus 15 kilograms. So these are some measures of masses of stuff. And it is easier to move or easier to change the velocity of things with less mass and harder to change the velocity of things with more mass. So because forces are vectors, if you have 2 forces, let me see if I can find another word. F1 and F2. That have magnitudes, that is lengths or sizes of F1 and F2, which of the following statements about the net force, net in this case means total, the sum, the net force are correct? The net force must have a magnitude equal to F1 or F2 plus F2. The net force can have a magnitude less than F1 plus F2. The net force can have a magnitude greater than F1 plus F2. And lastly, the net force must have a magnitude greater than F1. So if we're thinking about this, if this is F1, if this represents F1 and this represents F2, and they can point in various directions, let's go through these. Do you think the net force, the sum of the forces F1 and F2, remembering that they can point in various directions, they don't have to point in the same direction, does it have to have a magnitude equal to F1 and F2? F1 plus F2. Does this have to be true? That's correct. It doesn't have to be true. You could have, in fact, two forces pointing in opposite directions. So here, if this was F1 and this was F2, the magnitude would be, quite a bit smaller. The net force can have a magnitude that is less than F1 plus F2. Is that true? Can we manage a magnitude that is less than the sum of the two forces? I'm seeing nodding. That is correct. So this is correct. The net force can have a magnitude greater than F1 plus F2. Does that make sense? So if we have these two forces and we're adding them together and they can point any way, could you get a magnitude bigger than the two of them just lined up together? No. And then the last question is the net force must have a magnitude greater than F1. So if I point these any which way, do I have to have a greater magnitude that's greater than the original ruler? No. I mean, the simplest is just you point it opposite and it's effectively negative and subtract. So the only one of these that is correct is this one, B. So Newton's first law of motion is about what happens when you don't do anything to something, when you leave it alone. So if you stop pushing something, does it stop moving? In general. Well, in your day-to-day life, if I am, say, pushing this textbook across the table, when I stop, it stops. But I am not the only thing affecting this textbook. It's rubbing against the table. That's friction. So is the truth, things will only come to a stop if there is friction, if there is something causing them to come to a stop. If there's not any external force, an object will keep moving at constant speed in a straight line or remain at rest. And this is also known as the law of inertia. The Newton's first law says if you don't apply any force, or if the total force on this object equals 0, its velocity will remain constant. That's all it says. If you do nothing, the velocity remains constant. So what it says is that in order to change the velocity of an object, its magnitude or its direction, you have to apply some total force, some net force. And an inertial reference frame is one in which the first law is true. And the surface of the Earth is a good approximation of the inertial frame of reference. But if you're in an accelerating reference frame, that will not apply. It's not that hard to correct for an accelerating reference frame. You basically add a force. If you're in an accelerating reference frame, you create a force that looks a lot like gravity. And then you can treat it like it's an inertial reference frame. So there's some other things in there, depending on what's going on. Like if you have rotation. But generally, we're going to work in inertial reference frames. So we're not going to be doing anything in accelerating reference. So that's Newton's first law of motion. It's fairly straightforward. So if a car is traveling at a constant 45 kilometers per hour to the east in a straight line for 30 minutes, so its velocity is constant, it's 35 kilometers per hour east, and it's doing that for 30 minutes. During that time, what is the net force on this car? So what did we say happens if net force is 0? Yes. So velocity will be constant. So if velocity is constant, what is net force? No. So if velocity is constant, the net force will be 0. Because velocity is constant, the net force is 0. It works both ways. If there's no force on an object, its velocity will be constant. If an object's velocity is constant, there's no force on it. I mean, there's forces on this car, obviously, but they're all canceling out. First law questions are hard to write. So let's move on to Newton's second law of motion, which has an equation. So Newton's second law of motion. So if we have two equal weights, they'll exert twice the force. This can be used for calibrating a spring, like we did in the lab. Hooke's law. Newton's second law of motion helps you understand the relationship and what happens when there is a net force. So Newton's first law of motion is if there's no net force. Newton's second law of motion is for when there is no net force. So if we have a calibrated spring like this that we can measure force, we can do more experiments. We find that if we apply a force to an object, its acceleration is proportional to the force we apply. So here, when we apply F1, we get acceleration 1. When we double the force, we double the acceleration. So we find that acceleration is proportional to force, and it is inversely proportional to mass. If we apply the same force, and we double the mass, we have the acceleration. And this is consistent. Triple the mass, you'd make a third of the acceleration. So what we find is that force is proportional, not force. Acceleration is proportional to force over mass. And then what we do is we define our units such that acceleration is equal to force over mass. So we found that acceleration was proportional to force over mass, and we define our units of force such that acceleration is equal to force over mass. And this is more commonly written as force equals mass times acceleration. The units for force are newtons, so 1 Newton. So the unit is newtons. 1 Newton is 1 mass times acceleration, kilogram meter per second squared. So a force, an object can have several forces acting on it. So strictly speaking, this formula is the sum of all the forces is mass times acceleration. You add up all the forces on the object. So this would be the net force. And so the units for mass, acceleration, and force. In the SI system of units, mass is a kilogram. Acceleration is meters per second squared. Force is the Newton, which is 1 kilogram meter per second squared. In the CGS system, mass is a gram. Acceleration is centimeters per second squared. And force is a dyne. So that is a gram centimeter per second squared. In the British system, mass is a slug, which is a unit of mass that is technically correct, but no one uses. All the engineers use what are called mass pounds, which is the mass of something that weighs 1 pound. Acceleration is feet per second squared, and force, the unit of force is the pound. So when you measure your weight in pounds, that is the force of gravity pulling you down. So the easiest way to reduce your weight is to go to the top of a tall building where gravity will be slightly weaker. You will have reduced your weight without reducing your mass. So 1 Newton is 10 to the 5 dynes. It's about 0.225 pounds. Newtons aren't huge as a unit. A kilogram weighs 9.8 newtons. So some examples of some forces. The main engines of the space shuttle put out 31 million newtons. The pulling force of a locomotive is about 250,000 newtons. The thrust of a jet engine is about 75,000 newtons. The force to accelerate a car is about 7,000 newtons. The weight of an adult human is around 700 newtons. Roughly, to go to weight in newtons from mass in kilograms, you multiply by 10. We've been doing that in the labs. So 100 grams has a weight of about 1 newton. The weight of an apple is about 1 newton. The weight of a rose is about 0.1 newton. The weight of an ant is 0.001 newtons. So the net force acting on a plane has a magnitude of 1900 newtons and points in the positive x direction. If the mass of the plane is 860 kilograms, what is its acceleration? So the math is going to get a lot simpler for chapter 5 because we're not dealing with kinematics as much. So our force is 1900 newtons. Okay, that should have an X hat on it. Our mass is 860 kilograms. Our acceleration is what we'd like to know. So our net force equals mass times acceleration. So acceleration is force over mass. So 1900 newtons over 860 kilograms gives us 2.2 meters per second in the positive x direction. Got a little lazy with the vector stuff. Oops, sorry. Everybody got this? So here we have a hammer. Metal head of a hammer is loose. Tighten it, we're going to drop it on a table. This is actually one of the standard ways you tighten the head on a hammer. Should you drop the hammer with the handle end down, drop the hammer with the head end down, or do you get the same result either way? So do you want to drop it like this, so the handle will hit the table first? Do you want to drop it like this, so the head will hit the table first? I'm going to assume the head will hit the table first. Or do you get the same result either way? So what do people think? You can use the same technique for hammers and axes and other things. That is correct. So basically, you want the more massive part to keep moving. Yeah. So you want to drop the hammer with the handle end down because you want this more massive portion of the hammer to keep moving while the handle gets stopped by interacting with the table. And that's going to slam it into the handle and tighten it down. Here, if the hammerhead hits first, you only have the mass of the handle, the much lighter handle, to keep it going and tighten it down. Also, in fact, in a lot of cases, the handle will poke through. So if you do drop it like this, this will actually act to loosen the hammerhead, move it off. But if the hammerhead actually hits first, this would tighten. This is the best way to tighten. So when dealing with Newton's second law of motion, you often need to figure out what all the forces on an object are and how they add up, because you need to know the net force. So a free body diagram is a way to sketch the forces on an object. Basically, you sketch all the forces that are involved. You look at isolate the object that you're interested in. You choose a convenient coordinate system, because often it can be quite helpful to choose a coordinate system that you don't always have to pick y is up and x is horizontal. Sometimes it's convenient to set the coordinate system. If you have something on an incline, it's sometimes convenient to set your coordinate system up so it matches up with the incline instead of with the vertical and with gravity. But you want to then isolate the object of interest, resolve the forces into components, and apply Newton's second law to each coordinate direction. So basically what you do is you make a dot. So you sketch the situation, like if you had a car on a road, you might think about this. I've got some force, accelerating the car. I've got some sort of force of drag from the air or whatever. The ground is pushing up with a normal force. And then I have the force of gravity pulling down with the weight. I'll write that as a weight. W. And to draw a free body diagram, you just sort of draw a point and you draw all the forces around it. So we have some sort of force of acceleration, some sort of force of drag. We have the normal force up. Let me move this label. And the force, the weight down. So you can do it with all the forces like on the object, but sometimes it's easier just to draw a point and draw all the forces off of that. It makes it easier to break things into components and add them up. And then with kinematics, you know, much like with kinematics, you can apply Newton's second law in the x direction and the y direction independently. So here's an example. If you're holding a book, the force is on this. There's a force being applied upwards by the guy's hand, and a weight pulling it downwards from gravity. Those are the forces on the book. Similarly, the book on the table here. Well, if I took everything off the top of it, there's gravity is pulling it down. The table is pushing it up. So here's an example problem with multiple forces on a single object. We have Mo, Larry, and Curly pushing on a 752 kilogram boat that floats next to a dock. They each exert 80.5 Newton force parallel to the dock. What is the acceleration of the boat? If they all push in the same direction, give both direction and magnitude. And what's the magnitude and direction of the boat's acceleration if Larry and Curly push in the opposite direction to Mo's push? Okay, I did do that. So, I'll give you a little bit more time. So, part A, Mo, Larry, and Curly are all pushing in the same direction. So they all the force of Mo, Larry, and Curly is 80.5 newtons in the positive x direction. The mass of the boat is 752 kilograms, and we want to find the acceleration. So acceleration is the net force is mass times acceleration. So acceleration is net force divided by mass. So we'll add up our forces. The net force is just going to be the force of Mo plus the force of Larry plus the force of Curly all over the mass. So that's 80.5 newtons plus 80.5 newtons plus 80.5 newtons all over 752 kilograms, and it's all in the positive x direction. So the acceleration is 241.5 newtons over 752 kilograms, or 0.321 meters per second squared in the positive x direction. And if you want to do the magnitude and direction, the magnitude is 0.321 meters per second squared, and the direction is 0 degrees. Now, for part B, Larry and Curly are pushing in the opposite direction. So the force of Mo is 80.5 newtons in the positive x direction. The force of Larry and the force of Curly is negative 80.5 newtons in the x direction. Mass is still 752 kilograms. We're still finding acceleration. Calculation is essentially the same. Force equals mass times acceleration. So acceleration is force over mass. The force Mo plus force Larry plus force Curly over mass. But now force Larry and force Curly are negative. So this comes out to negative 80.5 newtons over 752 kilograms, or negative 0.107 meters per second squared in the x direction. So it will be 0.17 meters per second squared at 180 degrees if you wrote it out with an angle. Magnitude 0.107 meters per second squared. The direction is the negative x direction. Everybody got this? So, foamcrete is a substance that's designed to stop an airplane that's run off the end of a runway. That is a bad situation. And it does this by crumbling. So for example, suppose a 747 jetliner that has a mass of 1.75 times 10 to the 5 kilograms and an initial speed of 26.8 meters per second is slowed to a stop in 122 meters. So what's the magnitude of the retarding force exerted by the foamcrete on the plane? So for this problem, we're going to need to use one of the kinematic equations, which I will write out here. We're going to use, final velocity squared is initial velocity squared plus 2 times acceleration times delta x. And so we can use the kinematic information we're given to figure out the acceleration, and then use that to figure out the force. And it's just asking for the magnitude of the force. So that's just the size of the force, just the absolute value of it. So So we look at what we know. We know the mass is 1.75 times 10 to the 5 kilograms. We know our initial velocity is 26.8 meters per second. We know the distance traveled, delta x, is 122 meters. We know our final velocity is 0 meters per second because the plane came to a stop. So we want to find the force. And to find the force, we're going to need to find the acceleration. So we'll start by finding the acceleration. So velocity squared equals initial velocity squared plus 2 times acceleration times delta x. We solve this for acceleration. Acceleration is velocity squared minus initial velocity squared over 2 times delta x. Subtract initial velocity from both sides and then divide by 2 delta x. So if we plug in our numbers, acceleration is 0 squared minus 26.8 meters per second squared divided by 2 times 122 meters. And that gives us an acceleration of negative 2.94 meters per second squared. With that acceleration, we can now find out the force. Force equals mass times acceleration. So our force is negative. It's in the negative direction. We're interested in the magnitude. So minus F equals 175 times 10 to the 5th kilograms times negative 2.94 meters per second squared. So minus F is negative 5.15 times 10 to the 5th newtons. So the force has a magnitude of 5.15 times 10 to the 5th newtons. You can think of the F here as the force here, and it's negative because it's pointing opposite the x direction. You could also just take the absolute value because they're asking for a magnitude. So here we found acceleration to find force. Sometimes we'll use force to find acceleration to figure out movement. So you will have to use kinematic equations sometimes. Well, we still have 15 minutes, so I'm going to keep going. So let's talk about Newton's. We're still talking about Newton's second law. This is just a review. So here, if a pitcher throws a 1.15 kilogram baseball, accelerating it from rest to a speed of about 40 meters per second over a distance of 2 meters, we want to estimate the force exerted by the pitcher on the ball. This is a very similar problem to the last one. You have a starting velocity, you have a final velocity, you have a distance, and then you have a mass. So much like the last problem, we'll start by finding acceleration. We know the mass is 0.15 kilograms. Our initial velocity is 0 meters per second. Our final velocity is 40 meters per second. And delta x is 2 meters. We want to find the force, and to do that, we need to find the acceleration. So velocity squared is equal to initial velocity squared plus 2 times acceleration times delta x. Acceleration is velocity squared minus initial velocity squared over 2 delta x. So 40 meters per second squared minus 0 over 2 times 2 meters. This comes out to 400 meters per second squared. Force is mass times acceleration. So 0.15 kilograms times 400 meters per second squared gives us a force of about 60 newtons. Now, Newton's third law of motion is about how forces occur when two objects are interacting. Forces are always between two things. Forces always come in pairs, and those forces act on different objects. So Newton's third law says, if I push on something, it pushes back on me with an equal force in the opposite direction. So if object 1 exerts a force F on object 2, then object 2 will exert a force minus F on object 1. So for example, as I am standing here, I am exerting a force of, I am exerting a force downwards on the ground equal to my weight. The ground is exerting a force upwards with the force onto me, also same way, same quantity, but pointing up. Or here, when I push against the wall, I am exerting a force into the wall, and the wall is exerting an equal force into me. And we use this action-reaction all the time. It's how you manage to walk forwards. You apply a force backwards to the ground. So when I walk, I apply a force behind me to the ground, and the ground applies a force forward to me, and that moves me forward. So this is, how things move from walking and such. Or driving a car, same thing. The tires apply a force backwards to the road, and the road applies an equal and opposite force forwards to the car or to the tire. So here are some action-reaction pairs. The car applies a force on the ground backwards. The ground applies an equal and opposite force on the car. The Earth applies a force of gravity on a space shuttle, and the shuttle applies an equal and opposite force on the Earth from gravity. The person pushes on the refrigerator with a force F, and the object pushes back on the person with a force minus F. Similarly here, the person pushes on this mass with a force F, and that mass pushes back on the person with a force minus F. A lot of the time, this isn't super obvious because, say, you're pushing against the Earth or applying a pair of force against the Earth, and the Earth is enormously massive, so it doesn't move in any apparent way. So, though the forces are the same, the accelerations will not be unless the objects have the same mass. And you get some interesting things with contact forces. If you have two boxes and you apply a force to one side or the other, the contact force in the middle will be different depending on which side you push. Basically, the two boxes as a whole will accelerate with the same acceleration if you apply a force F on box 2 or the same force on box 1. But because the contact force in this case is accelerating box 1, it'll be bigger than the contact force here, which is accelerating box 2. So here is a problem with two groups of canoeists. So so here we have two groups of canoeists. So remember the force of 1 on 2 is equal to minus force of 2 on 1. That's the third law. And then here we have two groups of canoeists. They meet in the middle of a lake. After a brief visit, person in canoe 1 applies a force of 46 newtons to separate the canoes. The mass of canoe 1 and its occupants is M1, and the mass 150 kilograms, and the mass of canoe 2 and its occupants is M2, 250 kilograms. Find the acceleration the push gives to each canoe, and what's the separation of the canoes after 1.2 seconds of pushing. So we only have like 5 minutes left. I think I might just go through this and then I'll go over it. We'll be able to go over it again next time. The general idea is that the force on canoe 1 will be equal and opposite to the force on canoe 2. So the 46 person in canoe 1 will be applying 46 newtons to canoe 2 in the positive x direction. So that will effectively apply 46 newtons in the negative x direction to canoe 1. So mass 1 is 150 kilograms. Mass 2 is 250 kilograms. Force 2 is plus 46 newtons. We want to find the acceleration of 1 and the acceleration of 2. And to do that, we need to know what force 1 is. So to find force 1, well, the acceleration is going to be force equals mass times acceleration. That's what we're going to use to find that. But, and we can use that to find the acceleration of 2. So the acceleration of 2 is going to be force 2 over mass 2. So 46 newtons over 250 kilograms, or 1.8 meters per second squared. But to figure out the acceleration of 1, we need to find force 1. Force 1 will equal minus force 2. So force 1 ends up equaling minus 46 newtons. So force 1 equals mass 1 times acceleration 1. Acceleration 1 is going to be force 2 over mass. Damn it, typo. Ugh. Force 1 over mass 1. Force 1 over mass 1. So acceleration 1 is minus 46 newtons over 150 kilograms, or negative 0.31 meters per second squared. And the time is 1.2 seconds. And our initial position is 0 and our initial velocity is 0. We want to find the total separation, which is x2 minus x1. So we can plug that into our equation of motion, x equals x naught plus p naught t plus 1/2 acceleration t squared. X2 is going to be 1/2 acceleration 2 times time squared. So that's 1/2 times 0.18 meters per second squared times 1.2 seconds quantity squared. So 0.13 meters. X1 is 1/2 acceleration 1 times time squared. So 1/2 times negative 0.31 meters per second squared times 1.2 seconds squared. So that's negative 0.22 meters. X2 minus X1 is 0.13 meters minus negative 0.22 meters, or a total of 0.35 meters. And because of what the next lab is, and because a number of people aren't here today, I think I will be skipping the lab this week. We'll just continue on next week. So, so we will be stopping here today. I will stop the recording.